Okay, so this was a test I gave still in Washington and on carboxylic acids and lipids and esters. So I just put it under files, test related, unit 3. By the way, on the labs this week and next week, there was some confusion on that. Today we're doing 8A, which is the one in your lab packet on infrared spectrophotometry and melting point. Next week, we're doing 8B, which is the one I posted on files. Okay, that's the one on the acid equivalent. In fact, let me show you that. This is it here. Aspirin acid neutralization equivalence document. Okay, so that's for next week. And that's a standard pre-lab write-up. Basically, it's going to be 3 titrations. Okay, so let's look at go over some of this stuff. Like on every test, there's naming, there's intermolecular forces and reactions. So, okay, so we're naming these guys here. So let's see. This is an acid salt, a sodium acid salt. And let's see, how long is it? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so it's a sodium. And then we have a branch at carbon number 2. So sodium 2-hexanoate. Okay. That makes it an acid salt. Number 1. The O8 also is in naming a ester. So use it both those times. Okay, so we have an ester here. We have an OCO, double bonded O, single bonded O. And it is an ethyl. So you name the alcohol part first. And then the acid part second. So that's ethyl. And this is based on benzoic acid. And there's a branch at carbon number 2. 2-ethyl benzoate. Okay, we have another another ester. So alcohol, acid. So this is going to be ethyl. And that's 1, 2, 3, 4, 5. Pentanoate. Okay, this is a fatty acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And it's got 1, 2, 3, 4, 5. So there's two ways to name this. The common name is going to be EPA or eicosapentaenoic acid. The IUPAC name would be this guy down here. Icosa means it's got 20. Pentanoic. I did not spell that correctly. And these are the positions of the 5 double bonds. Now, the way to name it would be EPA. Using the delta, we're looking at 20 carbons long, 5 double bonds at positions 5, 8, 11, 14, and 17, counting from the acid end. It's also an omega-3 counting from the terminal end. So this is one of the common omega-3 fatty acids that you frequently buy when you go buy at the store, and it comes from fish oil usually. And these fish are a particular type of fish. These fish are always moving as opposed to the fish along the bottom, like halibut or flounder, something like that. Grouper, those fish don't have a lot of omega-3 fatty acids in them. The ones that cruise a lot do. That's the salmon, tuna, sardines, anchovies, smelt, any of those little fish. All big ones too, but ones that cruise around all the time. And then with salmon, most people throw away the omega-3 part of the salmon. Whenever you cook salmon, there's a dark streak along the side. That's where most of the omega-3 fatty acids are located. And most people don't like that. They scrape that off. That's where all the good oils are. Okay. So the E is the Icosa. And this says there are 5 double bonds and it's an acid. So Icosa is 20 carbons and is at positions 1, 2, 3, 4, 5, 6, 7, 8, 11, 14, 17, pentaenoic acid. And this would be also cis, 5 cis's, Icosa, 5A, 11, 14, 17, pentaenoic acid. How's that for a mouthful? And this is good old acetic acid. Okay. Any questions about number 5 up here? Yeah. I didn't specify here. If you put the common one down, I would have had to accept it. I may just say I'm writing both of them down. The common one, in my opinion, is almost harder. If you know the IUPAC one, they have the same, it works the same way on every single one. Well, the common name ones are all kind of different, but they're the old names. Remember when I started the lipid chapter, I said that's the oldest one. So they use a lot of common names. And the common names have no bearing. Like oleic acid comes from olives. That's where it gets oleic from, not because it's 18 carbons long with one double bond. I mean, so. Okay, so we're going to draw the following. Okay, hexanoic acid, double bond on number 1. And notice I didn't say cis or trans, so you can draw either one. Okay, so we have 6 carbons, double bond at carbon number 1. Does anyone see anything wrong with that? What about the bonds? 5, that's right. Well, that's an illegal structure. You cannot have a double bond, carbon number 1 for acids, because carbon can only take a maximum of 4 bonds. There are 5 there. Okay, bentanoate. Okay, that's a 4 carbon potassium salt. Okay, as soon as we see an O8, it's either acid salt or an ester. We go to the front, and if it's a cation, it's acid salt. If it's something else, it's then an ester. So this is going to be, start with benzoate. And it's a methyl. Okay, this is the one we just drew. This guy here. So this is 20 carbons. The tricky part in this is remembering And we know it's omega-3. So if you start from the back, the terminal end, and go forward, it's, in my opinion, it's easier. So it's got 20 carbons, so that's 20, 19, 18, okay? So that's 3 carbons in, that's the first double bond. I'm going to do all cis on here. Okay, so that's 1, 2, 3, 4. And then they alternate like that. And there are 5 of them. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18, 19, 20. So because it's an omega-3, you can use that trick to draw it. And because it's penta, we know there are 5 double bonds in there. Now, what is a wax? Remember, a wax is a really, really long alcohol, a really, really long carboxylic acid forming an ester. So we can have, let's say, C20, I mean, just really long ones. The main thing, though, is there's one ester as opposed to a triglyceride, or which has 3 esters in it. Simple steroid. Okay, remember on steroids we have those. I run out of room. So 6, 6, 6, 5. Okay, how would we make this? Now, some of these older tests, I would say, how do you make that? And basically, it's an ester. So it's a ethyl ester. The problem is a lot of people got confused by what I wanted there. So I don't put those on anymore. I still have reactions, but not in this format. Okay, so we need okay, with esters, again, there's always an acid part and an alcohol part. Okay, the alcohol in this case is a cyclohexanol. So that's the alcohol. And the acid is going to be a 1, 2, 3 carbon acid. Now, I don't know if you remember, but there are 3 ways to make esters. Okay. One way is with the alcohol and acid in an acidic environment. That's the least productive way. The other way is to use the acid chloride, which is going to look like this. And then the other way, so this gives the highest yield. And then the other way would be we would need to use the anhydride. So there's another question where I say, how do you make this 3 different ways? These are the 3 ways you make an ester. Alcohol, acid, alcohol, acid chloride, alcohol, and then the anhydride. Okay, so we have pentanoic acid. Two different ways, protonated and non-protonated. In an acidic environment, pH less than 7, the acid is going to be protonated. In an alkaline environment, it's going to be deprotonated because it's going to grab that hydrogen and form water. So in this case, pH 9 is very alkaline, so it's going to be protonated or ionic, non-protonated or ionic. And then in this case, we have an acidic environment, so it's going to be protonated. Okay, so this is DNA, and I wanted you to identify some different functional groups. So we've got okay, so that's an ester using phosphoric acid with the hydroxyl group on the ribose sugar. And then we've got some interesting stuff going on here, which is unit 4, which is called an amide. These are amino groups here. And so that's a deoxyribose sugar, these guys here. Those are phosphoric esters in yellow. Now, this was an interesting question. Very few people got this too. If you have something and it's solid in an acidic solution, say, and you added a base like sodium hydroxide, all of a sudden it dissolves. What do you think is going on? Why would something dissolve in water, first of all, as opposed to being solid in water? What is water? Is water polar or nonpolar? Polar, okay? So somehow by adding the sodium hydroxide, we made that solid more like water, more polar like water. So I want you to think back to this problem here. This guy here became more polar by putting it in a base. Hence it became ionic. More polar, so it dissolved. So that's where I was going with this. And hardly anyone got it. So basically, that solid was an acid, throwing in some sodium hydroxide, deprotonated it, pulled off the proton, made it very ionic, hence it became very polar, dissolved in the water. Okay, which compound can be the most soluble in water? Okay, let's look at this here. This is an acid, ether, alcohol, ketone. Which would be the most soluble? Going to be the acid. Then the alcohol. And then the ether and ketone would be about the same. And then the next question is, why would it be more soluble? Okay. Because this has both a ketone on it and a alcohol. So when you take the ketone here and the alcohol there, you put them together, forms a carboxylic acid. So the intermolecular forces are adding there. That's why it's more ionic. Okay, so we've got an acid, alcohol. One of the ways you form an ester is with an alcohol and an acid. So that means this is going to be a slow reaction because it's the slowest one. It'll still form an ester though. So what you're going to end up with is that. So here's the alcohol. Do that. acid side, alcohol side. And this would be a 1, 2, 3, 4 butanoic acid. With a double bond on carbon number 3. And this would be propanol. This would be propyl. 1, 2, 3, 4. Propyl 3 butanoate. Okay, so we have an ester in an alkaline or basic environment. So that ester is going to be saponified, and it's going to be saponified to the acid salt, which is going to be 1, 2, 3 carbon acid. Plus the alcohol, which is a 1, 2, 3, 4. So this would be butanol, and this would be and to name this ester 1, 2, 3, 4, so it's going to be butyl. So here we have another ester. We have OCO. And in an acidic environment, so that's can come apart to the acid part, alcohol part, acids, 2 carbon acid, so that's acetic acid, plus a 2 carbon alcohol, ethanol. Here we have an acid chloride plus an alcohol. It's going to form an ester. Okay, this problem says discuss the 3 ways to synthesize the following. Okay, it's an ester, 3 ways with the acid, acid chloride, and the anhydride. So the alcohol is a 2 carbon alcohol, so that means that's ethanol. Then we need to start with the acid, which is a 1, 2, 3, 4 butanoic acid. With the acid chloride, and then with the now in unit 4, we're going to have something similar to an ester, only because it's going to be called an amide, A-M-I-D-E. It's with an amino group, an N rather than an O. And there's 3 ways to make that one as well. Only one of them doesn't work. So there's really only 2, the acid chloride and the anhydride. Okay, so what's wrong with the following? What does omega-9 mean? Starting at the terminal end, we go into 9 carbons and there's a double bond. What does that mean? There are no double bonds, right? So that means this is a omega null set or just no omega at all. Stearic acid is 18 carbons, no double bonds, found in animal fat. Didn't I already ask this question? What's an emulsifier? Okay. Emulsifier has to have a on the same molecule. Okay. Give an example. We can have a stearic acid, for example. Stearic acid is 18 carbons. So it's where the polar end is going to be the acidic end, the nonpolar end is going to be the long 18 carbon trail of carbons. Okay, ALA is alpha linolenic acid. Okay, that's a C18, 3 double bonds, and it's an omega-3. So we're going to start from the end. And let's do ALA is a cis fatty acid. So we need 3 cis there. I'm going to go cis, cis, cis. And then we're going to go 1, 2, 3. Double bond. And we have 3 of them. And it's 18 carbons long. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So what carbons are on it? Okay, first of all, it's 18, 3, delta, 1, 2, 3, 4, 5, 6, 7, and it goes by 3s, 7, 8, 9, 10. 13 and omega-3. And this would be a octa, a 7-10-13 octa SC trienoic acid. And it'd be cis. And this is and these numbers are again from the acid end on the delta. How would you make this if you started with glucose? Well, that's a phosphoric acid ester. So the acid is going to be phosphoric acid. So the sugar is functioning as an alcohol. So here's the alcohol. And here is the acid. And this happens biochemically in the first stage of glycolysis in our body, when we metabolize carbohydrates. If you're starting with glucose, carbon number 6 gets phosphorylated with an enzyme called a kinase. Okay, so we have choline. What do we add to choline to get lecithin? Well, this is what lecithin looks like. Okay, so lecithin is built on a triglyceride. So that's the glycerol. That's functioning as the alcohol. These are this is stearic acid. And this is linoleic. But it can be any two fatty acids. It doesn't have to be those two. And then down here is why this is called a phospholipid is because we have phosphorus here forming a dual ester. And this is the alcohol here. And this is choline here. So what you need to add to choline is this part here. You guys have lab today? Okay. See you later. So you do need to know the structure of lecithin. Okay, SCFA is short chain fatty acids. This is a take-home test question because you have to look up the issue of this. But whenever you feed your microbiome a prebiotic, usually fiber, big illegal saccharide, something like that, your bacteria convert it to short chain fatty acids. And those have a lot of health benefits, a lot. So that's one real benefit of taking care of your microbiome. There's been a shift in years to consume more healthy fats. Okay, the healthy fats are mono unsaturated fats like olive oil, oleic acid. They oxidize. That's another take-home question, by the way. The more double bonds you have, the easier that acid will oxidize. And when it oxidizes, if there's more than one double bond, it forms something called a 3-carbon dual aldehyde. And those are very toxic. In fact, there's one school of thought when I was in graduate school, I almost worked for this principal investigator on that very project. If you take linoleic acid, it's got 2 double bonds, outside in the sun, you will make the stuff called malinaldehyde, 3-carbon double aldehyde, and it's considered carcinogenic. So people have put oil on themselves that smells like coconut to help protect themselves from the sun, are not doing themselves any benefit whatsoever. It's the opposite. So you have to be really careful on. Do you ever, who in here cooks? Anyone? Okay. Notice when you have a bottle of vegetable oil, when you get towards the bottom, the top is kind of sticky. That's because it's polymerizing. It's oxidizing. All those polyunsaturated vegetable oil fatty acids, triglycerides, are oxidizing, and that's what's forming the polymers. One of the reasons why restaurants are required to change their deep fryer oil fairly often is because of polymerization of the oil. You get big chunks of polymer in there. It's very bad for you. So they're required by state law to change it. Does anyone work in a restaurant in the back end? You're shaking your head? Huh? Yeah, and there's a big bin in the back parking lot where they dump the old oil. And people buy that for making biodiesel. But it's really, by the time they dump it, it's not very nice stuff. That's one of the reasons deep fat fried foods are bad for. One of the reasons. There are others as well. Okay, and then lastly, bacteria in the gut produce short chain fatty acids and medium chain fatty acids. How can these be enhanced? Okay, they can be enhanced by giving your bacteria more food, more prebiotic. That's the way they make it. The problem with medium chain fatty acids is that they put a lot of palm oil in there. And a lot of people say that palm oil is not particularly healthy for you. And it's just the length of the fatty acids. So those are all take-home questions. Okay, so that's it for that test. Now this is a good practice test. You'll have 2 hours. In fact, we may have a little more than that because our lab is going to be short next week. I'll give you 2.5 hours if you need it. So there's structures, drawing them, naming them, reactions, and intermolecular forces, IMS. Your unit 4 is going to be very similar to unit 3. It involves proteins, though, instead of lipids, and it involves that nitrogen ester-like called amides. It's similar. Okay, that's what I wanted to cover today is that practice test. Now on Tuesday, I'm going to. Would you like me to go over another practice test on Tuesday or start unit 4? Okay, so this helps going over examples. Okay. All right, that's what we'll do on Tuesday. Okay, that's it for today.